What are we going to do? Okay. So there was a little topic in there that we want to revisit. We talked about, let's see, this is what I want to get a head start. So this is what you guys were supposed to do, something like this. Even if you didn't do it, I hope that you know how it works. The 3 different checks for 0 order, first order, and second order. Okay? So, like, this was we talked about this is called, get it, time concentration data. Time concentration data. It's wonderful. And we said that a 0 order check is along the y-axis, it's the concentration of A or whatever, in this case NO2. For check for first order, it's the natural log, okay, of the molar concentration. To check for second order, it's the inverse of the molar concentration. Okay, very good. So that's all well and good if you only have 1 reactant. But what if you have 2 reactants? And I'm going to show you kind of a little trick around that. So if we have 2 reactants going to form products, then we know that actually the rate law expression looks like this. Rate is equal to some rate log constant K times the molar concentration of each reactant raised to their reaction order, M and N. Okay, or, well, I usually put M and N. This says N and P. But okay, so here's the trick. The trick is basically we somehow need to make the molar concentration of B, which is a reactant, constant. And it's weird to make the molar concentration of a reactant constant because by definition reactants get used up, right? Okay. But if we can make B constant, then our rate law expression we can pull that B in with the K. Okay? So see what's done here is we pull the B in with the K because they're both constant now. And I'll show you how do we get it constant, okay? And raised to its reaction order. But again, this is a special case when it's constant. And then anytime you see that prime, K prime, that's a pseudo-constant. The prime makes it a pseudo-constant. So now our rate law expression looks like this. Rate of the A reacting with B, and we're going to hold B constant, is equal to some pseudo rate law constant, K prime, which brought in our B, which is constant, times the changing molar concentration of A raised to its reaction order. Then we can go ahead and test for 0 order by plotting the concentration, test for first order, the natural log, second order, the inverse of it, all with regard to time. Look for a straight line. Yep. So the way we're going to do it, or we can do it, Thursday's lab may be the one listed, but it might be a different one. So just hold tight. I'll let you know on Wednesday. But if we do the one listed, we're going to actually have to use this technique in lab on Thursday. So the way to do it, or a good way to do it when we do it in this lab, I think that's listed for Thursday, is we have the molar concentration of B way big, okay, and have the molar concentration of A like normal. So for instance then, if A and B react in a 1-to-1 relationship, okay, then let's just say that, how do I say this? B is, if we make B so large, B very large, 0.100 molar, A normally small, 0.00100 moles per liter. Okay, if A is entirely consumed, then basically B doesn't even have a dent in it. Okay, so B is held constant. We can go ahead and vary the concentration of A and find its reaction order, basically. So that's the trick. On to part 4. So we're only going to do part 4. There's not a whole lot of slides here, but there's a few problems I want to take a look at the end. And you guys need to be doing these problems. Don't get on that habit, because if you are, then I'm going to stop outlining the problems, honestly, because it took me, that's my job or whatever, but like 30 or 40 minutes to outline these. So if we're not going to do them, then...
Well, we really did attempt it. We
okay.
did spend like 30 minutes on it, seriously.
Okay. Very good. That makes me feel better. You're in good shape. Okay. So I like these problems. So let's see if you like them. And, okay, so time concentration, one run, time concentration. It's different than multiple runs with different initial concentrations that we looked at before. Okay. All right, so these sort of problems typically come in kind of this is what we're going to get after. Basically, you'll want to know time. That's the letter T, right? Time required to get to a certain concentration. The other type of calculation is, broadly speaking, to how much do you have left? How much A do you have left after a given amount of time? And we're going to focus on, like the slide says, first order and second order. And actually, I printed out some of the slides, so I'd have them handy. Okay. We are going to be using these equations for first and second order to work those problems. So do you remember this one? And actually, here today, before we leave, I'm going to go ahead and give you the Unit 2 equation sheet, so you can kind of start to, it looks something like what I'll give you. Well, there's another form of that, and actually I brought, you don't have to dig it out if you don't have it handy. But this last law of logs down here, it says basically if you take E, which is a weird number, E raised to the natural log of x, that's equal to x. I mention that because basically if we want to get rid of that natural log sign, we can take E raised to the ln of A over A0 is equal to E raised to the negative KT. Okay, what that would be equal then is A over A0 is equal to E raised to the negative KT. Multiplying both sides by A0, we get the molar concentration of A at any time T is equal to the initial concentration times E raised to the negative KT power. Again, that's first order. And everybody's calculator should have that E raised to the x, and that's what you would use here. All right, so that's first order. Second order, the time concentration, integrated time concentration equation looks like this. If it's second order dynamics, okay, or second order mechanism, it has this relationship between the original concentration, A0, any concentration A at time T. All right, so I have that handy. Exhibit 1. All right, so let's work a couple problems. Or one problem anyway. No, I think a couple problems. There's a lot of words up here, and you're going to see it kind of diagrammed on the next page. But if we focus on kind of picking it apart here, okay, the fact that it's first order, okay, means that I'm going to be able to use these two equations on the top. Okay, let's see. The rate constant, that's K, right? So basically, they're giving us K is equal to 1 over 1.65 years. Remember that units of the rate law constant, K, will be inverse time if the overall reaction order is 1. And basically, this is just A goes to decompose. Okay, so there's only one reactant. All right. So then it says, if a 0.0060 molar solution is stored, blah, blah, blah. Does this make sense that that actually is going to be our A0? That's what it starts out to be. Starts out as. And then our 2, now, I will just say that if I was you working these problems, whenever it says first order, you can even write these in the margin of your problem. Okay, these are what you're going to use. And it depends which one you're going to use. Like it says, what will be its concentration after 3 months? What will be its concentration? That one, right? After 3 months, we're going to plug in 3 months for the T. The second one is how long will it take the concentration to reach blah, blah, blah. Okay, so this blah, blah, blah is our concentration of interest. This is our A. Okay, that's going to be our A for that problem. and we're solving for T. So actually, for that one, we can go ahead and do the top one, because we'll know A, that's that 0.0010. Of course, we know the original concentration, that was that 0.0060. We got K because it was given, we can solve for T. So that's basically how we're gonna do those. Okay. So since it's first order, since it's first order, we know that we can use this integrated time concentration equation to work the first part. So this is always a good idea. Notice that in the blah, blah, blah of the problem, it didn't say A decomposes, it says an antibiotic decomposes. So I went ahead and said, anytime you see A in this problem, that's the molar concentration of the antibiotic. All right, so this is pulling out the stuff that we know. The A0 is 0.0060 moles per liter. The rate law constant K is 1.65 per year. And in the first problem, the time of interest is 3 months. That's specific to that first problem. So right away we have a time issue, right? Because our K is in per year and our time is in months. So we got to either go the months to a year or the year to a month, okay? So I'm going to go from those 3 months, I'm going to scale that up to a year. So an exact relationship is there's 1 year is exactly equal to 12 months. So scaling up my time of interest, that 3 months makes sense. It's a quarter of a year, right? 0.250 years. Okay, and so I think we're ready to substitute. So substituting in for the first order time concentration equation, the concentration of interest is equal to the initial concentration, that 0.0060 moles per liter, times E raised to the negative KT. So raised to the negative 1.65 per year. And also then is that raised to that times 0.250 years. That was the time of interest. And, you know, don't hesitate to kind of break these down. You know, multiply this out first. It's going to be negative. And, you know, take E raised to that power, and then take that times this if you want to kind of break it out. We should be allowed 2 significant figures. Okay, so might want to play around with that. That's a good one. You should get a molar concentration of A at that time of interest should be decreased to 0.0040 moles per liter. Not bad. Okay, so let's look at the other one, where we were given a concentration of interest and we're supposed to find time. So if you're ever supposed to find time, this is the one that you want to use. So we can go ahead and rearrange that, solving for time. So time is equal to negative 1 over K times the natural log of A over A0. And again, this little green box to tell you what we've got going on here. The first 2 terms are the same as they were with the first problem. We still have the same initial concentration, 0.0060 moles per liter. We still have the same rate law constant, K is equal to 1.65 times 10 to the negative first years. And now the molar concentration of interest is 0.0010 moles per liter. So we're going to substitute all that stuff into our equation. Aren't you glad you get the equations for the exam? Just to give you a little confidence in it. Okay, so substituting in, we have the K, we have 1 over negative 1.65 years inverse times the natural log of A over A0. So A was our concentration of interest, 0.0010 moles per liter, and A0 was that initial concentration, 0.0060 moles per liter. again, get some practice at this with your calculators. Sometimes with the calculator, I'll do it a couple times, see if I get the same answer. So round is two significant figures. Or I guess three. I'm giving myself three here. The time is 1.1 years or 1.09 years. I would take either one of those. But just to kind of remind you how, what units cancel, moles per liter, of course, have canceled. Here we have units of reciprocal years in the denominator. So anything in the denominator that is in the denominator of the denominator, like this, basically comes out in its units of years. Any questions? Cool. Very practical stuff. Okay, so just to remind you, now we're going to switch gears, I think, and look at something that's second order. All right. So again, basically, we have one thing, one reactant, because they're saying that butadiene reacts with itself to form a dimer. So instead of C4H6, it's C8H12. Okay. Second order reaction kinetics. So get your second order reaction kinetics ready. Okay. Let's see, the temperature is fine. We'll talk more about temperature. Actually, temperature is a player, and our K will change with temperature. We'll talk about that later. They give us the K at this temperature. The rate law constant K at this temperature is 144 liters per mole per hour. Remember, we said that if it is second order, it's going to have units of liters per mole and time, also in the denominator. And that's what we have here. Okay, so it looks like the 0.0200 would be its initial concentration. So we only have one equation, so it's not really pick and choose here. But I think this will work out just fine. So we have K, they gave it to us in the problem. For the first problem, it says, what is the concentration after 1 hour? So that looks like a time, okay? So we'll have 1 hour there, and we have the rate law constant K. We have the initial concentration, A0. The thing is we're going to have to kind of, at the end, kind of solve that. We're going to have the inverse of A, so we're going to have to fix that. But I usually leave 1 over A by itself till the very end, and then I kind of take 1 over what I've got to get A by itself. So for the next one, it says how long will it take for the concentration to decrease to 0.0020 moles per liter. In that case, that's our target concentration, okay, the 0.0020 moles per liter. Of course, we have A0, the initial concentration. We have K, and now we're solving for T. So to work the first one, it looks like this. We rearrange and solve for, like I said, I'm going to leave it as 1 over A, and I'm going to fix it at the very end. So A is our concentration of interest at time T. So let's go ahead, and there's the green box. Oh, yeah. And then remember, like I said, the molar concentration of antibiotics equal to the molar concentration of A. That's what this is. Kind of making sure we're kind of clearly defining variables when we work the problem. So for that first problem, actually for both problems, the initial concentration of A is 0.0200 moles per liter. Rate law constant is 144 liters per mole. And hours is also in the denominator. And for the first problem, the time of interest is 1.00 hours. So let's plug. Okay. So again, leave the concentration of interest as the inverse is equal to the rate constant, 144 liters per mole per hour. Okay. Times K times T, our time of interest, is 1.00 hours. You can already kind of see how hours cancel there. plus the inverse, or 1 over the initial concentration of 0.0200 moles per liter. Okay, so here again, if we look at how our units are working, okay, so units of hours cancel, and we're left with units of liters per mole. Notice that we have actually in the denominator of the last term moles per liter. If we want to bring that up, actually that does make it liters per mole. So if you go ahead and give this 3 sig figs, you'll end up with 194 liters per mole. And again, it's good you're getting these in your notes because you can go back and kind of make sure your calculator's doing like it should. So do you see where now to get the real A, we basically have to take 1 over 194? Okay, so if you take 1 divided by 194, that will give you A. Okay, and on your calculators, if you do that, rounding it to 3 sig figs, you'll come up with 0.00515 moles per liter. Let me go ahead so it doesn't go away. That last step. I almost think I'd like these slides. I need to add one more step. So that's the first of 2. So the second problem was we were given the molar given the molar concentration of interest, A, and we were supposed to find T. So if we rearrange this solving for T, we have 1 over K times that quantity, the inverse of A minus the inverse of A0. So again, for the second problem, that's 0.020 moles per liter. We still have the same rate law constant, 144 liters per mole per hour. And the concentration of interest is 0.0020. There's too many 2's there, I think. So ready to plug in. The time then would be equal to 1 over 144 liters per mole per hour, that's the K, times the quantity, the inverse of A, the concentration of interest, that's that 0.0020 moles per liter, minus the inverse of A0, 1 over 0.00200 moles per liter. And again, we have moles per liter in the denominator, so bringing them out, that actually would cancel or would make it liters per mole. Or we could just leave them down there and go ahead and let our liters cancel, our moles cancel, okay? It looks like we have just units of hours in the denominator of the denominator, which is units of hours in the numerator. So 2 sig figs. When you do that, do it right, you get 3.1 hours. This actually, you might look for your calculators. A lot of times they'll have 1 over x, and that comes in handy there. So if you kind of figure out how to use it in your 1 over x key. Just be careful. If you're like me, these chemistry problems are not as easy just to eyeball and say, oh yeah, that makes sense. Now, does it seem reasonable that in a little over 3 hours we would only have 0.0020 moles per liter left? I can't eyeball that and say yes. Okay. Any questions about those? And like I said, you'll have these on the test. All right. So for the homework that y'all looked at and just, oh goodness. But there was a question that said half-life, and I said, don't worry about it. But it's really not too hard. Basically, what half-life is, it's a time, and it basically is the time required to get to half of your initial amount. Half-life, that's what it is. So half-life has the symbol T 1/2, that's half-life. Okay? So that's the time when your concentration of interest is half of what you started out with. Okay? Half-life, T 1/2. Okay, so these were the other that this is my exhibit 2 and exhibit 3. And actually, when I give you, the thing that has a box around it, when I give you your equation sheet for Unit 2, you're going to see this. But let's just kind of look at first order. We said that first order reaction has this relationship with regard to the concentration at a given time divided by the initial concentration, natural log of is equal to negative kT. Well, if we go ahead and by definition, we know that we've met half-life if your A is half of your A0, then your time is half-life. So let's go ahead and make those substitutions. Okay. So basically here in a minute, instead of A in the numerator, you're going to see A0. You can already see that my A0s are going to cancel. Okay, so this is just specific for first order. Okay, so my A0s cancel, kind of cleaning things up. So I end up with the natural log of 1/2, this is for first order reactions, is equal to negative K times the half-life time. Well, not quite done yet. Going ahead and solving for the half-life. The half-life is equal to 1 over negative K times the natural log of 1/2. And there's a cool thing, I can't remember how it works. But if I want to, I think of it as basically absorb that negative sign into this natural log. That's going to make it basically the natural log instead of 1/2, the natural log of 2. Okay. So I absorb that negative sign basically in the 1/2 of the natural log. That made the natural log of 2. We still have K in the denominator, and that's it, box time. Okay. So if it's first order, a few things here. Notice that if it's first order, the half-life does not depend anywhere in there. You don't see the initial concentration of A. It's independent of the initial concentration of A. I'm going to put another note here on this slide because actually in your homework you're going to use this to your advantage. But do you see where if for some problems that you are given, I'll say if given this being K, or sorry, not K. If you're given the half-life and they tell you it's first order and know it's first order, oops. Do you see where you can find this? You can get the rate law constant K if you're given the half-life. It's first order. So that in the box will be on your exam that you take a week from Thursday. So we're going to do a similar proof. This is first order. Let's go ahead and look at second order, and things come out different. Okay, not so surprising. But before we do, thanks. But before we do, let's look at half-life. You can have multiple half-lives. So if this actually is a first order decomposition of di-T-butyl peroxide, but it's first order is the point. So can you see where if it starts out at 800 the units are partial pressure, units of partial pressure. Notice when it gets to 400 millimeters of mercury, partial pressure, then half of it's been used up. It went from 8 to 4. And so that time right there, 80 minutes, would be its first half-life. Its second half-life then would go from 400 to 200 millimeters of mercury. Okay, so its second half-life is 160 seconds. Minutes, excuse me, 160 minutes. Its third half-life goes from 200 to 100, and it's out here. 240 minutes. Okay, so first half-life, second half-life, third half-life. All right. So yeah, let's do a similar kind of substitution like we did before. Okay. So you recognize, maybe, maybe not, the inverse of A minus the inverse of A0 is equal to KT. That's second order reaction kinetics. So if we substitute in 1/2 A0 for the inverse, or for A there, then the T will be the special half-life. So it looks like this, kind of cleaning things up on this slide. Okay, it looks like this. Okay, further cleaning things up. Oh, there you got your final kind of what's going to be on your equation sheet for your exam. So for second order, the half-life is equal to 1 over K, also in the denominator, is the initial concentration of A. Okay, so here, if it's second order, it does depend upon the initial concentration of A. So kind of like I told you before, can you see if second order kinetics, if you're given this and given the initial concentration, you can find K. So I have those handy. That's for first order, second order, and this was my first sheet. So here is what I've given in the past for the equation sheet. So you can see we haven't talked about all of them yet, but we've talked about quite a few of them. And I don't know if this is how it will look or they'll be more scrambled, but if we just kind of look at this together, can you see where it's really kind of organized? Okay. Does this, remember we talked, does this look like zero order? The first one? Remember, in order to do a first order test, along the y-axis, you go ahead and plot basically the molar concentration of A versus time. So that would be 0. The next row is actually first order. Okay. And then the third row is second order. And then actually we talked about the 2 half-lives, and to me, that next one down there, what do you think? Is it first or second? Natural longitude.
First.
It is first. Looks good to me. First order for half-life for first order, and then that last one is second. So yeah, this other stuff down here we're going to be talking about. I'm not sure if we'll get to it this week or probably by the end of this week. All right. So this could be handy to have when you're doing homework if you want to kind of have it. So, okay. So here are some tips on working these problems in general. Just kind of keep your wits about you. There's different equations for different reaction orders. Make sure you don't blow that off, right? I'm talking to myself too, not just to you guys. Okay. And there, one kind of hint to get to a reaction order, if it's not given to you, but if you're given K, the units of K should give it away. Now, the units of K are specific to the overall reaction order, but if you only have one reactant, then it should not be too bad. So I have this little hot link here to remind you how that works. So remember, if the units of K are moles per liter per time, then it's zero order, and there's only one reactant. I should say the overall reaction order is zero. The overall reaction order is 1 if the units of K are per time, like we had the per year, that was first order. If your overall reaction order is 2, then it will be liters per mole per time. So. Those are a couple of hints. So these are actually, these couple of hints we've been talking about. I hope you kind of read through the gray. So if K isn't given to you, but you have a half-life, okay, and if you have the half-life and it's first order, then by golly, you can, if you have a half-life and you know it's first order, you can get to K, remember? If it's second order, you'll need the half-life and the initial concentration. You can also get to K if you, and this is actually, we're going to see an example of this here in a minute when we look at your homework that's due for Wednesday. You can also get to K if you were given the concentration after a given amount of time. And I don't know if I need to put it, I'll just say it in so many words. That last one, basically you revisit these up here, whether it's first order or second order, and you plug in your initial concentration, your A, and your T, okay, and you can get K. So that's by revisiting the original time concentration, integrated time concentration equations. And we'll also look at an example of these, I think, okay, that if you look at, and I'll hold this one up because it's bigger, but for first order, there's this cool thing where basically we have the natural log of the ratio of the concentration to the original concentration, okay? And actually, that is just itching to be a mass fraction, okay? Or percent, parts per 1. And we'll do an example of that in your problems that are due. Okay, so let's look at your problems that are due. And there are a couple that you'll need to plot, but I think it'll be a little more straightforward. And if you've already kind of done some lifting looking at ones that were due today, it'll probably just kind of work just fine for you. Okay. I don't think it really took me 20 minutes. It felt like 20 minutes. These are fun, though. I like them. Okay, so here's 17. It says it's first order. So again, feel free to use this to do your homework if you want to. It's first order, and they give the half-life. First order, they give the half-life. Remember, one of the hints where we can get to K, and actually that's one of the first things I'm going to do, is get to K using that half-life for first order. Okay. This is a classic. Okay, you're not given K, but you're given half-life, and you can solve for K. So in orange this time, what you can see next, since it's first order, I went ahead and wrote the half-life for first order, we just talked about. And then we have 2 equations for first order. I'm not sure which one I'm going to use. But usually you have time to write this down too. Okay. So we can go ahead and get to K. And actually, that's all I'm going to tell you, get to K that way. Now, A says, what percent of a sample A remains unreacted 900 seconds after a reaction has been started? Okay. So here's my hint there. Anytime you see what percent, think A over A0 percent. A over A0 times 100. Okay? So that's looking like this, okay? So basically, if you can solve for this ratio, you're almost there. You're going to leave those variables together, a over a0, okay? Notice in this case, they gave us a time, okay? We got the k earlier, so basically we have t and k, and we're going to solve for this a over a0. Now here's the other catch I want to show you. That the law of logs that I gave you, it's actually the same law that I mentioned a minute ago. This law down here, okay, if I want to get to, if I have the natural log of x and I want to solve for what x is, okay, basically I can get to that if I take e raised to the natural log of x. That will give me x. That's exactly what I'm going to do here. I'm going to take e, I know it's weird, it's cumbersome, e raised to the natural log of this ratio is equal to that ratio. Okay? So I have to do the same on both sides though. So basically I'm going to have a over a0 is equal to e raised to the negative kt. Okay? Oh, I didn't mean to do that. Which looks very similar to the exponential form that we use. Nope. Yeah. Okay. So don't get mind boggled. But so here, the law log, I told you what the law log is. Okay. So actually, that's just my hint for a. So leave it as a over a0. Don't solve for them individually because you can't. It doesn't want them individually. It just wants to know the percent. So solve for that and leave it like that. For the last one, for B, it says, what is the rate of the reaction at the concentration of interest is 0.50 moles per liter. And don't lose sight of this. It's easy to. Basically, just go back to your rate law expression. We said rate is equal to the rate law constant K, which we got, times the molar concentration of interest. Okay, so that one's easy to lose track of what you need to do. Okay. So for this one, it's first order also. So I went ahead and jotted down everything we know about first order. We don't have to use the half-life this time. And it gives us, it says initially, blah, blah, blah. So that's my initial concentration. A0 is 0.800 moles per liter. And it gives us, after 54 minutes, the molar concentration is down to 0.100 moles per liter. Okay, 2 questions are asked there. And we can use these if we have K. But here, this was the example where I said, if you're given the concentration, like you are the 0.100 moles per liter at some time t, which is 54 minutes, actually we can plug back into here, a over a0 natural log of is equal to the time, 54 minutes, and solve for K. That's how we're going to kind of somewhat backdoor get our K. We're going to get our K first, and then we're going to proceed with the problems. Then, with K in mind, we can turn our attention to A. It's question A. It says what time, and if you ever have to find a time, you're actually going to use this first form. So we're going to use that same form again to go ahead and work the problem. Using the same A0, now with a new A, the concentration of interest is 0.025 molar. Again, use that equation and solve for T. The next one, what is the reaction rate when A is equal to given that? So we're just going to go keep it simple. Rate is equal to K times the molar concentration at that given time. We have K, the molar concentration is 0.025 moles per liter. First order again, just kind of jotting down what we know. I did go ahead and jot down the half-life because it looks like we're going to have to use it. I see B refers to half-life. So we're given the initial concentration, the 0.816 moles per liter, and we're given the concentration after a certain time. So actually we can use that initial concentration. We can use that initial concentration and this concentration here at this time and solve for K. So again, it's kind of like back what we did with the last problem. So before we can work the problem, we have to do a pre-problem, okay, to get to K. Okay, so once we have, that's A actually. And then B is what's the half-life. And so we have K, so we're just going to substitute in here to get the half-life. Okay. And then C is what time will the concentration be 0.235 moles per liter. And again, anytime you're supposed to get to time, use this one. It seems like, well, I'm ready to use this one, but again, get to time, we'll use this one. Of course, we have the molar concentration of interest is that 0.235 moles per liter. Initial concentration stays the same. We have K, and let's solve for T. And then D, finally, you get to use that second form of the first order, okay? Anytime you're supposed to get to a concentration of interest, given the time, this is the form that you're going to use. So it says at 2.5 hours, we're going to plug that in for T. We already have K. We're going to take E raised to the negative KT times the initial concentration of A to get to the concentration of interest at that time. All right, so this one, I went ahead and made the columns for you ready to graph. Okay. So basically they have some time concentration data. And the first thing is show that it's a first order. So guess what? You're just going to have to do one plot. Okay, and first order check is what? The natural log of the molar concentration versus time, and look for that straight line. Now you're going to need to plot it because then you're going to use that slope this time to get to K. Okay, so B is what's the value of K. You're going to get it from your plot. And then the last one, I would go ahead, you could use your graph, I think, but I would go ahead and use, since it's first order, it has this relationship, and the concentration at any time T is this. Okay, so it said, what if your time is 750 seconds? What's the molar concentration? Okay, so you plug in for that. And then two reactants, A and B, and thank goodness it's zero order with regard to B. And it's second order with regard to A. So our rate law expression then doesn't have B in it. Does that make sense? Because B raised to 0 power is 1. So our rate law expression is rate is equal to K times the molar concentration of A squared. And of course we only have one equation. It gives us K, that's cool. Okay, and what is the rate of the reaction if the concentration of A is blah, 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 and the concentration of B is blah, 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 but who cares, right? So this one's actually not too bad. We're just ready to plug. Okay, basically, we're given K and given more concentration of A. I had to double check my notes. I'm like, really? Yeah. So it's not too bad. That's it. This one is, again, kind of, I could have done the columns, you know, time, concentration, but you need to do that. And now it's kind of like you'll need to use Logger Pro. And, of course, to check for second order, it's 1 over the concentration along the y-axis. And the slope will be positive this time, and the slope will be your K. And so, actually, that's B. And then all of those questions kind of go together, okay? So in each one of those questions, we can use this relationship where this concentration of interest are these. So there'll be 3 different problems. Of course, the initial concentration was the 0.100 at time 0. And we know K from the slope, and we're supposed to solve for T. All right. Very good. So, you got my number if you run into any snags that you're like, or you might have you should have each other's number too.